traffic this morning along the Keighley Gardner Guy Valentine.
It's a bit of a battle for drivers without cover. I'm talking if you don't have any shade, you're fighting some pretty bright sunshine.
And also caution on Highway 7 going eastbound.
And northbound Don Valley Parkway on the ramp to eastbound 401. We've got a disabled vehicle.
June the 14th, 2002. It was just another busy workday with all the usual hustle and congestion. With all the close calls and near misses that people all over the world have come to accept as the normal level of risk in everyday life. But on that day, high overhead and behind the sun, what no one saw coming, what no telescope on Earth was able to see against the blinding light, was an asteroid big enough to destroy an entire city. From behind the sun, asteroid 2002 MN came hurtling towards Earth, faster than a speeding bullet. It shot past, less than a third the distance to the moon, and nobody saw it, until 3 days later, when the rock emerged from Earth's shadow into the night sky, going away.
It looks like the Earth just dodged a bullet. Actually, it was an asteroid. Scientists say it blew by last week at a distance they describe as a close shave.
The airline industry would call this a near miss. Scientists who study asteroids and comets called it a problem.
The threat of asteroid impacts on the Earth is very real. We know that throughout history this has happened. The craters we see on the moon are examples of the kind of impact history that the Earth has had. But it also happens very rarely. So it's a very unusual kind of hazard. It's a hazard in which the risk in any one year is very low, but it does happen, and if it really did come about on our watch, it could end civilization.
These cosmic bullets originate on the far side of Mars, in the main asteroid belt, where a bracelet of celestial debris circles the sun. Millions of rocky fragments, building blocks of a planet that never quite came together when the solar system was formed. What's often depicted as a busy cosmic junkyard is actually more like a big empty speedway. The rocks are far apart and moving very fast, ranging in size from pebbles to boulders to rocks the size of Mount Everest. Occasionally, the tug of Jupiter's enormous gravity drags an asteroid off course, causing it to crash into another asteroid. Some veer away into new orbits that cross the paths of Mars, Earth, Venus or Mercury. Another ring of debris called the Oort cloud is the source of most comets, which are big, rocky ice balls that orbit the sun and cross the paths of the inner planets. All the inner planets and our moon bear the scars of numerous asteroid and comet impacts.
We do get hit all the time by pieces of debris from asteroids and comets. In fact, 40,000 tons of cosmic debris plummets into the atmosphere every year. We see them every night as shooting stars. They don't hit the Earth very often, but when they do, clearly it isn't just going to be a matter of a shooting star seen in the sky. So it is inevitable. It's only a matter of time before the next big one hits us.
Even small rocks can make a big impression. In 1908, about 2,000 square kilometers of Siberian forest were instantly flattened as an asteroid exploded near the Tunguska River. The impact site was so remote, researchers had to mount a wilderness expedition just to find the place. When they arrived, there was no crater. Paintings, based on eyewitness accounts, described a fireball. A horrendous explosion in the sky.
Didn't actually come crashing down to the ground. It exploded maybe 5 to 10 kilometers up in the atmosphere, and that made a big blast wave in the atmosphere, and that is what did the damage.
All this was caused by a relatively small asteroid, somewhere between 50 and 100 meters across. Roughly the same size as asteroid 2002 MN, the one we couldn't see coming. Tunguska's 2,000 square kilometer blast wave would have leveled London. But as bleak as the thought of cosmic collision may be, there is at least a glimmer of hope.
One of the special things about the asteroid impact problem is that unlike the weather or earthquakes or other natural hazards, we, at least in principle, we could do something about it.
And when we know one's coming for us, our claim is that the technology is available today to stop it.
On the Earth, we've got active geology, we've got volcanoes, we've got earthquakes, we've got continental drift, we've got rain, we've got wind, we've got storms, we've got snow. All of those things erode away craters, and that, in some ways, actually fools us into thinking that, indeed, the Earth doesn't get hit as often as it actually does.
Counting craters on the Moon and then estimating how often the Earth gets hit can be a pretty sobering exercise. One scientist who made that kind of calculation was astronomer Ernst Opic, who published his impact estimate back in 1951. The general public, however, paid little attention to the science or the implications. But one individual who did take the issue to heart was Lembit Opic, the astronomer's grandson, who got himself elected to Parliament.
My grandfather is the reason why I carried on in politics, what he initiated in science. In essence, he was a pioneer. He saw the danger of asteroid and cometary impacts with the Earth, and he had the courage to speak up about them. And he did that at a time when it wasn't really taken seriously, in the 1950s and 1960s.
After years of pushing and prodding, Lembit Opic convinced the British government to commission a comprehensive scientific study of the asteroid and comet threat. The expert conclusion was, the threat is indeed real.
Now, the government has set up a task force to examine the risk of an asteroid hitting the Earth.
Still, skeptical politicians might want to get on the bus and take a trip to the Natural History Museum. Ask any schoolchild who's been there recently, and you'll hear a fascinating and truly scary tale about what happened to the dinosaurs.
The dinosaurs were alive here. They were dead when this sediment was deposited, and this layer is one of the most unique layers in Earth history.
In 1980, the discovery of iridium beside a layer of clay which marked the end of the age of dinosaurs led Lewis and Walter Alvarez to publish a theory that a huge asteroid or comet had hit the Earth 65 million years ago and wiped out the dinosaurs. But for this concept to be confirmed, there had to be a crater. There may be tons of dinosaur bones in these dry canyons, but where on earth was the big crater? Just the kind of mystery a budding young scientist would love to solve.
When I went back to...
Off the coast of Mexico's Yucatan Peninsula, Dr. Alan Hildebrand investigated a huge gravity anomaly discovered by oil drillers back in the 1950s. Put that together with a semicircular magnetic anomaly, and you get a massive crater, 180 kilometers across, near a little village called Chicxulub Pueblo. Most of the crater is underwater now. Erosion and continental drift have covered the visible evidence. But 65 million years ago, this was ground zero.
This object would have fallen through the atmosphere in just a few seconds. It's going through the sky, it would have been brighter than the sun. As soon as it contacts the surface of the shallow sea in Chicxulub, of course, it starts propagating the shock wave down into the planet, and it keeps pushing into the planet, and it only gets stopped maybe about 30 kilometers down. The pressure wave would have traveled around the entire planet in the atmosphere. You could have heard the impact on the other side of the planet. The giant impact fireball rising out of the hole, it would have risen, say, 10,000 kilometers above the surface of the planet. Near the impact site, it would have been so hot, it would have evaporated the clouds and been hot enough to make the forest, even a green forest, begin to burn.
For Alan Hildebrand, finding that crater pretty much clinched the argument. Planet Earth had been all but sterilized by a rock the size of Mount Everest.
3/4 of the species of large animal life went extinct.
We have made the case. We've got the qualitative information and we've got the statistics to show that there is a very serious risk.
If you wanted to save planet Earth from cosmic disaster, where would you find people with all the right stuff to do the job? Well, Houston, Texas might be a good place to start looking. This town has that rarest of breeds, the space cowboy. Houston is home to NASA's Johnson Space Center, where rocket science is a way of life and astronauts learn their trade.
If you could roll me 90 and then go down, I'll come in on my side.
Behind a swimming pool big enough to swallow an apartment block, you'll find a small research lab where the rocket engine of the future is being built and bench tested.
Yeah, very nice. Question is, how big is the plasma going to go from here to here?
Dr. Franklin Chang Diaz is one of the lead researchers, as well as an astronaut with 7 shuttle missions under his belt.
And in fact, there was a time in one of my flights where we got hit by very tiny micro meteorites, perhaps, or some sort of orbital debris, which made little tiny dents or little craters in the windows of the shuttle.
Well, that you did well there. Yeah, I did it. You already well there. Yeah, I did it.
First-hand experience with rocks in space gave birth to a new idea and a dual purpose to Chang Diaz's work here. His rocket engine has been developed for long-distance missions to Mars, or as far away as the icy moons of Jupiter. But it could also be used to push a dangerous asteroid out of harm's way.
I am concerned enough to think that we need to not waste time arguing about it as to whether it's real or not. I think we need to move ahead. If this is a threat which has a very low probability, all it takes is one, and we are history.
But before we can send a spacecraft chasing after a rogue asteroid, we have to know where to look for it. In the American West, if you drive across the desert to the White Sands Missile Range in southern New Mexico, you'll find the most powerful and effective asteroid hunter on Earth. Scientists here have tested everything from rockets to the very first atomic bomb. Today, across the valley floor from the Trinity bomb site, the US Air Force has installed one of the world's most advanced telescopes. This state-of-the-art technology was developed by MIT's Lincoln Laboratory as part of the Star Wars anti-missile defense system. These may not be the world's biggest telescopes, but they clearly are the best when it comes to finding deadly rocks in space. This is LINEAR, the Lincoln Near-Earth Asteroid Research Facility.
On a given night when we scan the sky with this, we'll find perhaps 10 to 12,000 moving objects in the sky. Now, most of those are main belt asteroids and as such don't represent any danger to Earth. But on the other hand, something like half of those will be brand new discoveries, and buried in there will be 1 or 2 near-Earth objects.
Because the Earth rotates, the sky is always moving overhead. To get a clear picture of an asteroid, you have to make the sky stop moving. And you do that with a telescope that can track or follow the stars. This way, you can take time-lapse pictures that isolate the blur of fast-moving asteroids against a crystal-clear sky. It then records these pictures like a TV camera on a computer chip that has 20 times more detail than the picture you're now watching. The linear computer deletes previously known stars and planets, leaving a less cluttered time-lapse sequence of the new discoveries. At the end of each night shift, Linear's thousands of new discoveries are emailed to the International Astronomical Union's Minor Planet Center at Harvard University. A team of only 3 scientists must cope with the avalanche of new sightings, searching for potentially hazardous asteroids or comets. Computers make a rough calculation of an asteroid's orbit, but it's up to Brian Marsden to estimate the level of risk.
They may be reporting 50 or 60,000 observations from one night, and it takes a while to get through that. But so we look first at the fast movers and see if there's anything interesting there. H is equal to sine delta.
We do sometimes get close to 70 or 80,000 observations a day, almost 1 per second. There are some days when we effectively have 1 observation per second.
Even with fast computers, Marsden's team can make only a preliminary calculation of each asteroid's orbit. 5 shots in one night cover only a tiny segment of an asteroid's orbital path.
You can't solve for the orbit completely from that, but the fact that you're seeing motion over a half an hour or an hour, something like that, does allow us to get a partial solution for the orbit.
Refining the orbit gets complicated. When 2002 MN shot past, its trajectory was warped by Earth gravity, and scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, had to add that to their calculations.
Here's an animation I put together of the asteroid last year, which was discovered after it passed by the Earth.
An elite team of mathematicians and celestial mechanics is now working full-time on a computerized warning system.
Our orbit animation, you can see how when it returns out to the asteroid belt, the close approach to the Earth has changed its orbit, and it's no longer returning to the same place it started.
Because 2002 MN will circle around the Sun and come past us again, the NASA Orbital Mechanics team will have to adjust the calculation in order to know whether it will ever pose a danger to Earth at some point in the future.
So here we've zoomed in on the Earth-Moon system and we're looking down. You can see how close it came to the Earth. It went over the top. And how you can actually even see the bend in the trajectory. So it's a great example of how a close approach to the Earth, or in fact any planet, can be used to, or can significantly change in orbit.
To know where an asteroid is likely to be in the future, you need a model of the solar system. Mechanical models that show the relative motions of the Sun and planets have been around since the early 18th century. They're called orreries. What the celestial mechanics at NASA had to do was create a new digital model. One that includes the gravitational attractions of all the planets and the Sun, and all the other forces that can affect where an asteroid might go.
You just compute what forces are acting on this particular asteroid from all the planets and many of the minor planets in the solar system, and then we can actually trace the motion of that object around the solar system for hundreds of years.
For scientists, the acid test of their mathematics came when a strange new comet raced toward Jupiter. A stream of cosmic bullets that would shock and amaze millions here on Earth. In the spring of 1993, the eyes of the world turned almost in unison towards a doomsday rock like no other. From the far side of the solar system, it flew in a death spiral toward the largest planet. Gene Schumacher, his wife Carolyn, and their colleague David Levy had discovered an odd-looking streak of light that turned out to be a fractured comet. 21 large chunks of icy rock and cosmic dust heading towards Jupiter.
We knew we had something very unusual. It was so unusual we were a little unsure just what we were dealing with.
NASA asked Paul Chodas and his team to calculate the orbit and predict whether this new comet would actually hit Jupiter.
And it started off at some 60%, and before long it was 90%, and this was a year before impacts. As the impacts approached, we continued to predict not just the impact probability, which went very high, but where and when the comet fragments would hit the planet. And it was a prediction months in advance. And as we got closer and closer to the impacts, I kept wondering, well, is the math right? Will this actually happen the way it was predicted?
A giant comet is on a collision course with Jupiter.
Everybody on Earth who was paying any attention wanted to see if the comet would actually hit Jupiter.
We have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
NASA's Hubble Space Telescope set its sights on the planet, and the pictures of what happened next were truly stunning.
Hey! Right there! Oh! Get it! Wait. Oh,
And then the impacts occurred. We were within minutes of getting the right answer on the time of impact, and the location of impact turned out to be just right.
Over the next week, 20 more fragments of the comet crashed into Jupiter, some leaving scars as large as the Earth.
Bang on its cosmic schedule, the comet's first impact was recorded by NASA within the last hour.
When fragment G slammed into Jupiter, releasing an amount of energy equivalent to about 6 million megatons of TNT.
In the wake of SL9, a group of concerned scientists gathered in Italy for a brainstorming session. They created a brand new international organization called the Space Guard Foundation.
Okay, I'm going to join.
To promote the discovery and study of near-Earth objects.
Some people imagine that there are lots of astronomers out there scanning the sky looking for incoming comets and asteroids, and that, of course, is not true. In fact, until recently, there was hardly anyone out there looking.
It's going to glow for about a half an hour and set everything on fire around you.
But whose job is it to defend planet Earth? Weapons scientists from the United States and Russia had already held a series of meetings and came up with their own ideas about how to deal with the impact threat.
Blow off some material, you get a reaction in this perpendicular direction.
The military establishment under Star Wars had created a whole lot of devices, or at least concepts, for weapons in space and devices in space. And in the early 90s, when the Star Wars program was looking a little bit iffy, I think there was some motivation for them to try to apply their technology to this newly discovered hazard from asteroids and comets.
The military approach to the problem proved to be controversial. The notion of sending nuclear weapons into space generated an immediate backlash.
Edward Teller was proposing that we blow up an asteroid to show that we could protect the Earth, and I thought that was a pretty crazy idea. Blowing up an asteroid with a big bomb has a lot of problems associated with it, violating treaties, taking a single asteroid and making a swarm of smaller asteroids. It seemed like it was more interest in bombs than it was a serious interest in defending the planet. For NASA, on the other hand, NASA obviously is the natural agency to discover the threat and the objects, but they say, no, planetary defense, that's a military obligation and not an obligation of NASA.
Not NASA, not the military. Just when it seemed planetary defense was nobody's job, a tiny speck in the sky would set off doomsday alarms around the world. On a winter's night, the 6th of December 1997, a dim streak of light moving through the constellation Cancer was captured by a telescope in the Arizona desert. Big enough to destroy civilization as we know it, asteroid 1997 XF11 seemed to be heading towards Earth. The initial sighting by the Kitt Peak Observatory in Tucson, Arizona, was relayed to the Minor Planet Center at Harvard University in Cambridge, where a computer made the first rough calculation of the orbit. They were pretty sure it would miss the Earth on this pass, but it would be coming round again, and it looked like there could be a problem in 30 years.
There were indications of close approach to the Earth in 2028. That was about 45,000 kilometers, which really was rather close.
With only a handful of sightings, the orbit calculation remained very rough. It was hard to tell where this rock was going. So Brian Marsden posted a bulletin asking astronomers around the world for more observations before the rock became too faint to see.
I was saying, hey, get your big telescopes onto this. On the one hand, we're only going to be able to observe it for another month or so. We want to improve the orbit calculation and find out exactly how close it is coming.
But one line in the bulletin said that the chance of a collision was small, but it was not entirely out of the question. Within hours of the website posting, reporters discovered XF11, and doomsday headlines screamed around the world. Because the close approach in 2028 would put the asteroid nearest to Europe, London newspapers focused on the exact moment life on Earth might possibly end.
Pictures of it on the internet show it as a tiny moving blob. Scientists have calculated its path in the year 2028.
Watch very carefully. September, October the 28th, the two coalesce.
But at NASA's Jet Propulsion Laboratory in California, the orbital dynamics team thought there must be some mistake.
Asteroid's orbit was affected by it. To my great surprise, when we ran our software, it said that the probability of impact of this particular asteroid in 30 years was essentially zero.
As it turned out, the end-of-the-world asteroid would miss the Earth. That big rock in space posed no threat after all. A frantic hunt through the archives at NASA had turned up photographs of XF11 taken 8 years earlier.
And as soon as those were placed into the orbit determination process, they confirmed the fact that there was no chance that it could hit the Earth in 30 years.
The public at large was not understanding uncertainty in this. They wanted an immediate answer. Is it going to hit us or not?
But people were paying attention. One side effect of the false alarm was that public and political awareness of the threat had been raised. 2 months after XF11, new hearings were held in Washington, and NASA was told to speed up the science of asteroid detection. Finally, it seemed, there was a political will to do something. Congress gave NASA a 10-year deadline to search the skies and get a fix on the largest of the doomsday rocks. They called it the Space Guard Survey. While astronomers geared up to search the skies, Hollywood was going into overdrive.
I would go to every dinner party and I would say, are you aware what would happen if a comet was actually on a collision course with the Earth?
Oscar-winning screenwriter Bruce Joel Rubin was hard at work on the remake of a sci-fi classic. The new film, called Deep Impact, would be a Steven Spielberg production.
An army of scientists work desperately to build this giant rocket, this modern Noah's Ark, to carry a few picked survivors of our doomed civilization.
I think the thing that was hardest for me was the realization that people would have to be chosen to survive.
Let's take the ship away from them! Come on!
probably a very, very small percentage of human beings would be left on the Earth able to survive something of the intensity of the comet that hit and destroyed the dinosaurs. So I felt making this movie is not just a mission to tell a good story, it's to change minds. It's to let people go, this is something real. This can happen to us. This movie is a wake-up call. It's not just a Hollywood movie, it is pointing at you.
As Hollywood released Deep Impact, telling the world in no uncertain terms that cosmic collisions were no longer just a cosmic joke, real-life professional asteroid hunters were making movies of their own. But instead of using cameras, they worked with delayed Doppler radar. Take the same technology behind a police radar system, jump the power to 400,000 watts, and you've got NASA's Deep Space Network, with huge multi-dish systems, like the Goldstone tracking station in California's Mojave Desert.
This is the main room of the pedestal of DSS-14.
The first time radar astronomer Stephen Ostro bounced a signal off a rock in space, a wobbling blot of pixelated data bounced back. What looks like digital gibberish spoke volumes to Steve Ostro.
Radar really does three things at once. One, it works at long wavelengths, so you're sensitive to structure on large scales and metal concentration. The other is you can make pictures. And you can't do this from the ground in any other way. You make pictures of objects, and then we take a sequence of pictures, and we go through a computational process to produce the 3D models. That's the second thing. The third thing is that it makes very precise measurements of distance and speed.
When the 1,000-foot radar dish at Arecibo in Puerto Rico bounced a beam off an asteroid called Castalia, the data was translated into a 3D computer model. The very first radar movie showed how Castalia spins and revealed that it was actually two massive chunks of rock held together by weak gravity. Every time they made the trip to Goldstone for a new radar target, Ostro and his team were like kids reaching into a box of chocolates. They never really knew just what they would find. Asteroid Cleopatra, shaped like a dog bone, was roughly the same size as the state of New Jersey and was made almost entirely of metal. Echoes from asteroid Tutatis produced images of a rocky, cratered surface and a wobbling, tumbling spin.
Every single one of these objects that we've made a shape model of is very different. This is Tutatis.
From a telescopic smudge of light to a 3D shape model, radar gave them physical details and the first clear idea of what asteroids are really like. In the year 2000, the radar movie crew developed a dark and mysterious new image, Asteroid 1950 DA, a big rock that gave everybody a bit of a shock.
Once we got the radar data, we began the normal process of just seeing how far in the future we could predict this thing before the uncertainties in the orbit blur out. And in this case, we could go over 880 years into the future. And what was startling about that case was the impact probability turned out to be non-zero.
Non-zero means there is a chance this rock could hit us. On March the 16th, in the year 2880, 1950 DA will cross the Earth's orbit. Will it hit us? The odds? 1 in 300. If 1950 DA does hit the Earth, the most likely point of impact would be at sea. Of all the big asteroids discovered thus far, this is the most dangerous one we know. Eric Asfaug and Stephen Ward have created a computer model of the impact.
Yeah, it's kind of funny how this started. It was with the movie Deep Impact, and I was getting phone calls. Lots of people were getting phone calls about the movie, whether it was accurate, the big cresting tsunami coming across.
The concept here is that this asteroid, which is about 1 kilometer across, will hit the ocean at 17,000 miles per hour, and it'll blow a hole in the ocean about 19 kilometers across and all the way to the bottom. And so when this huge hole of water gets blown into the ocean, the water will run back in again, and it overshoots and then collapses and overshoots many, many times, and each time it pumps out a wave. So it starts out hundreds of meters high, comes ashore on the coast of North America at about 50, 60 meters. Up toward Canada, Grand Banks, it's about 40 meters. 20 meters here in the coast of South America, and about 15, 20 meters all the way over to Europe. These waves would run inland about 4 kilometers. So pretty much everything within 4 kilometers from the beach would be covered up repeatedly. And so we'd pretty much be wiped away like you're scrubbing the floor. You know, just scrub like this, and it's pretty much we'd all be carried back out.
In February 2001, a NASA spacecraft called Near Schumacher made the first ever landing on a chunky, pockmarked rock named after the Greek god of love. Asteroid 433 Eros is 33 kilometers long and 13 kilometers wide, one of the largest near-Earth asteroids. The pictures were spectacular. The data will take years to process. Proving that they could land on an asteroid was a major achievement, but in the end, they still don't know much about what's inside. How dense? How tough? How brittle or crumbly is it? What would happen if they gave it a good shove? The surface appearance of any dark and mysterious object can be very deceiving.
So these two spheres, as far as I can tell, have exactly the same mass, the same compressibility, the same color. If I were a spacecraft orbiting these and these were asteroids, I'd be very hard-pressed to tell which was which. Yet, if I dropped them from a height, and only one of them bounces, really illustrates the fact that one of these responds elastically and one of these responds like a lump of clay. And it's critical to really go and find out what's inside before we even start thinking about moving these things around.
When a 3D model of the asteroid Castellier got smacked in a computer simulation, a problem occurred. An impact with the same energy as the Hiroshima bomb turned Castellier into a pile of rubble, but did not deflect its trajectory in any significant way. But there are other ways to apply force to deflecting an incoming asteroid. Using the power of the sun to push dangerous rocks out of the way may not be so far-fetched after all.
This is a typical near-Earth asteroid. Its name is Galevka. It's about half a kilometer across. It's a hazardous asteroid. Its most likely fate is going to be to strike the Earth someday. Thousands of years from now.
Modern-day researchers like Eric Asfaug say the idea of a giant orbital magnifying glass to burn space rocks could work.
You create a vapor plume in one direction, and that starts the asteroid moving in the other. It's a very gradual process. It's not going to happen instantaneously. You need to know where this guy is 100 years or 50 years ahead of time. But if you do, you've got all the time in the world for a satellite to sit there, no human intervention whatsoever, and it'll gradually shove the asteroid into a different orbit, and it'll miss the Earth.
Some of the technology to do this already exists. Take an inflatable parabolic antenna the size of a tennis court, convert it to a solar collector, and use it to focus sunlight on an asteroid. The Russians have built and are testing a giant sail that captures the minute pressure of sunlight. Just attach the sail to an asteroid and let the rock hitch a ride to someplace else. But using the sun to save the Earth means waiting for nature to do the work. If we don't see an asteroid until the last minute, solar power would be too little, too late. A nuclear electric plasma engine could push an asteroid out of harm's way. The rocket technology at this NASA lab in Houston, Texas could provide the power for a space tugboat. A group of astronauts and aerospace engineers is designing the B612 mission to prove that asteroid deflection can be done with existing technology.
These are rockets that have very tiny amounts of thrust, but they are so frugal in the use of propellant that we can keep the rocket going for periods of the order of a year.
Building a better rocket engine is only the first step. Figuring out how to latch on to an asteroid, point it in the right direction, and push without losing control is the really tricky part. After years of research, NASA finally had it, the first complete draft of a plan, a demonstration mission, to save the planet.
We can move the asteroid off the impact with the Earth 10 years later so that it misses the Earth, and not just miss it randomly, but miss it very precisely so that we don't simply pass on the problem to our grandchildren.
Midway through 2003, the Space Guard survey had reached the halfway point. A little more than half of the kilometer-sized near-Earth asteroids had been located, and the news was mostly good.
For the 60% that we have already found, I can tell you that there is not a single one that poses a danger. For the 40% that we have not yet found, I can tell you nothing. One could hit tomorrow. Not very likely, but until we've found them and cataloged them, we won't know.
But finding the really big asteroids, those 1 kilometer monster rocks capable of ending human civilization, is only the first part of the challenge. There are an estimated 50,000 smaller asteroids that are big enough to cause tidal waves or destroy vast regions of the Earth.
A 200-meter asteroid happens maybe once every 10,000 years, but that's like 600 megatons to 800 megatons exploding in one place.
Recall the small 60-meter rock that exploded over Siberia in 1908? Well, even though it could have destroyed a city like London or New York, rocks that small are not included in the current Space Guard survey, meaning no one is officially looking for them.
Which, of course, is the same thing as saying that chances are enormous that a Tunguska-sized object will find us before we even see it coming, as happened in 1908. That is likely to happen nowadays, that we won't see it coming.
There has been talk of expanding the search to include smaller asteroids. It'll take more and bigger telescopes and, of course, more money. But until we do, we'll have no idea where those city-killer rocks are.
Evolution on Earth has proceeded in part because every so often a global catastrophe comes along, pushes the reset button, and new things happen.
It wiped out the dinosaurs 65 million years ago, and at the time, we mammals were just furry little creatures burrowing around in the ground, and an asteroid or a comet impact took out our principal competition.
I guess we are saying implicitly, if not explicitly, that we want to do away with that natural cycle.
We've had enough evolution. We like ourselves on the top of the ladder. And we can do something which will change cosmic evolution from this point forward in terms of life on Earth.
Dinosaurs ruled the Earth until a big rock wiped them out. The question is, will another rock do the same to humanity?
Let's get a couple good pictures here.
humans are the first species with the potential to block a doomsday rock and switch off the evolutionary reset button.
People very often say, look, you're just a doomsayer. You think that these awful things are going to happen. I'm not that way at all. I'm entirely optimistic. The way in which I view asteroids and comets and the possibility of them hitting the Earth is that it's a great challenge. Thank goodness we've realized the hazard and the danger before the next one happens. It's given us time, we hope, to do something about it.
Scientists can study the sky and find the dangerous rocks ahead of time. Astronomers can do the math and predict the orbits. People have the desire and the right stuff to do the job. There's a whole new field of science that could give humanity an option the dinosaurs never had.
By on this busy, crowded planet. As life changes and evolves from second to second. At the same time, the arc of the human lifespan is getting longer. 67 years is the global average, up from just 20 years in the Stone Age. Modern science provides a humbling perspective. Our lives, indeed even that of the human species, are just a blip compared to the Earth, at 4.5 billion years and counting, and the universe at 13.7 billion years. It now appears the entire cosmos is living on borrowed time. It may be a blip within a much grander sweep of time. When, we now ask, will time end? Our lives are governed by cycles of waking and sleeping. The seasons, birth and death. Understanding time in cyclical terms connects us to the natural world, but it does not answer the questions of science. What explains Earth's past, its geological eras and its ancient creatures? And where did our world come from? How and when will it end? In the revolutions spawned by Copernicus and Darwin, we began to see time as an arrow in a universe that's always changing. The 19th century physicist Ludwig Boltzmann found a law he believed governed the flight of time's arrow. Entropy, based on the second law of thermodynamics, holds that states of disorder tend to increase. From neat, orderly starting points, the elements, living things, the Earth, the Sun, the galaxy, are all headed eventually to states of high entropy or disorder. Nature fights this inevitable disintegration by constantly reassembling matter and energy into lower states of entropy, in cycles of death and rebirth. Will entropy someday win the battle and put the brakes on time's arrow? Or will time stubbornly keep moving forward? We are observers and pawns in this cosmic conflict. We seek mastery of time's workings, even as the clock ticks down to our own certain end. Our windows into the nature of time are the mechanisms we use to chart and measure a changing universe, from the mechanical clocks of old to the decay of radioactive elements, or telescopes that measure the speed of distant objects. Our lives move in sync with the 24-hour day, the time it takes the Earth to rotate once. Well, it's actually 23 hours, 56 minutes, and 4.1 seconds, if you're judging by the stars, not the sun. Earth got its spin at the time of its birth, from the bombardment of rocks and dust that formed it. but it's gradually losing it to drag from the moon's gravity. That's why, in the time of the dinosaurs, a year was 370 days, and why we have to add a leap second to our clocks about every 18 months. In a few 100 million years, we'll gain a whole hour. The day-night cycle is so reliable that it has come to regulate our internal chemistry. The fading rays of the sun, picked up by our retinas, set our so-called circadian rhythms in motion. That's when our brains begin to secrete melatonin, a hormone that tells our bodies to get ready for sleep. Finally, in the light of morning, the flow of melatonin stops. Our blood pressure spikes, body temperature and heart rate rise as we move out into the world. Our days and our lives are short in cosmic terms. But with our minds, we have learned to follow time's trail out to longer and longer intervals. We know from precise measurements that the Earth goes around the Sun every 365.256366 days. Much of the solar energy that hits our planet is reflected back to space or absorbed by dust and clouds. The rest sets our planet in motion. You can see it in the annual melting and refreezing of ice at the poles, in the ebb and flow of heat in the tropical oceans, or seasonal cycles of chlorophyll production in plants on land and at sea. These cycles are embedded in still longer Earth cycles. Ocean currents, for example, are thought to make complete cycles ranging from 4 to around 16 centuries. Moving out in time, as the Earth rotates on its axis, it makes a series of interlocking wobbles called Milankovitch cycles. They have been blamed for the onset of ice ages about every 100,000 years. Then there's the carbon cycle. Plants capture it from the air or the sea. It finds its way into soils or ocean sediments as plants decay or as waste passes out of the food chain. The arc of this era is defined by the life cycles of stars, which vary according to their sizes. Stars shine because gravity crushes matter into their cores. The energy released pushes outward and balances the inward force of gravity. This battle between energy and gravity is raging in stars all around the universe. But in large stars, about 10 million years after their birth, gravity begins to gain the edge. When the mass concentrating in the core of the star reaches a critical threshold, the core collapses in on itself. The energy released in the collapse causes the star to explode in a blast of light and debris that's visible across the cosmos. In the wake of this supernova, shock waves can cause nearby clouds of dust and gas to collapse and ignite to form generations of smaller stars, like our Sun. A byproduct of star formation, solar systems form in the collapse of the surrounding solar nebula. The life cycle of planets, especially those in close, is tied to that of their parent stars. As stars like our Sun age, they grow hotter and more luminous. Billions of years from now, that will spell the beginning of the end for our home planet. As raging solar winds begin to blast away at our atmosphere, surface water will gradually disappear, rendering Earth uninhabitable. Finally, the Sun will begin to swell, growing so large that it actually envelops the Earth. Friction with the Sun's outer edges will cause this once blue world to gradually spiral inward. Unless they are large enough to go supernova, most stars end their lives in more of a whimper than a bang, as shown in this gallery of dying stars captured by the Hubble Space Telescope. In time, solar winds push their outer layers so far out, they blossom in spectacular displays. That's just what happened about 12,000 years ago to the star that spawned the famed Helix Nebula. On the inside, spokes of denser gas stubbornly resist the star's relentless winds. The star itself is now a dim, cooling remnant called a white dwarf. It's the size of Earth, but about 200,000 times more dense. This is likely what's in store for our Sun. A distant civilization may scan it for planets, but by then they won't see Earth. This battle between energy and gravity repeats in every corner of a galaxy like ours, with gravity drawing gas clouds into stars, and stars burning themselves out on a variety of timescales. In time, though, as the mass of the galaxy collects in successive generations of small stars, it will grow dimmer and dimmer. Some galaxies will see a temporary rebirth if their mass gets stirred up and combined with another. That's what's destined to happen to our Milky Way. At just about the time our Sun begins to swallow our planet, any remaining Earthlings will see the stars of the Andromeda Galaxy looming above the plane of our Milky Way. As shown in this simulation, the two are likely to tear each other apart. If it's a direct hit, the stars in both galaxies will gradually join together in a gigantic galactic puffball known as an elliptical galaxy. All the turbulence of the merger could stimulate a wave of new stars being born, reinvigorating the new, larger galaxy. Dust-ups like this, in which galactic neighbors merge, will be common as the era of stars moves into its later stages. But a wholesale thinning out of the universe is inevitable in filaments of galaxies. These voids are like ever-expanding bubbles. Where the bubble walls touch, you can see filaments of galaxies. As the bubbles grow, the filaments will stretch and break. The distance between galaxies will widen at a faster and faster pace. Eventually, no matter where you are in the universe, you will see only a few isolated clusters of galaxies huddled together, with little connection to anything else, and few clues to how they got there. At more distant reaches of time, tens of billions of years from now, the sky will grow darker and darker as everything recedes away from everything else. A good place to be in those long twilight years of the stellar era is a place where gravity and energy have forged an extended truce. Perhaps a place like this. Not much larger than our planet Jupiter, a red dwarf is one of the smallest and dimmest stars in our universe. They have been shown to harbor planets close enough that their dim rays can sustain liquid water and life. Brown dwarfs and red dwarfs form the vast majority of stars in our galaxy. In fact, combined, their mass exceeds that of all the large stars. Because they burn so slowly, They'll be the final beacons of the majestic age of stars, an era that will extend out to 100 trillion years. Even as their host galaxies grow dim, another process will begin to transform these small outposts. Over time, chance encounters between objects will perturb their orbits, sending some toward the center of the galaxy and others out into the void. In this way, galaxies may gradually evaporate, with ever denser concentrations of matter accumulating in their cores. As that happens, the universe begins to take on a new character. Welcome to the degenerate era, in which the universe is populated by red and white dwarf stars steadily cooling, and by the charred remains of supernova explosions, neutron stars. Even though these dead stars have used up their nuclear fuels, they continue to produce small amounts of energy. They scoop up and annihilate dark matter particles that manage to stray into their grasp. Here is where cosmic evolution slows to a crawl. It's expected that protons, the building blocks of all atoms, will slowly degrade, turning into subatomic particles that then decay into photons. All the protons in existence date back to the early moments of the universe. Their eventual decay will mark the end of the degenerate era. Around 1 billion, billion years after the Big Bang. That's a 1 followed by 40 zeros. Our picture of what happens after that depends on what we learn in the coming years beneath the border of France and Switzerland, in one of the largest physics experiments ever undertaken. 100 meters underground, the Large Hadron Collider was built to accelerate particles in opposite directions through a giant ring 27 kilometers around. When they reach nearly the speed of light, scientists will bring them into ferocious collisions. One goal: to define the final time horizons of our universe, as well as the final moments of its most persistent objects. Black holes, ranging from millions to tens of billions of times the mass of our Sun, occupy the centers of large galaxies today. As those galaxies age, over trillions of years of time, much of their mass will spiral toward the center and into the jaws of ever more ravenous black holes. Conceivably, these black holes could end up weighing as much as a galaxy. But when they finally stop growing, will they too be subject to the ravages of time? According to the physicist Stephen Hawking, the answer is yes. He proposed a theoretical process of decay that scientists are hoping to test in high-energy particle collisions at the Large Hadron Collider. The idea is that throughout our universe, particles of opposite charge constantly well up in the vacuum of space. They normally destroy each other. But when this happens at the event horizon of a black hole, one particle can be pulled in while the other escapes. That has the effect of slowly siphoning energy and mass from the whole. If this is true, then even black holes are eventually doomed. But finding out for sure is not easy. Creating a micro-black hole, it seems, will take more energy than any Earth-bound collider can pack. That is, unless there's more to nature and to gravity than we've thought. The key lies in whether the universe we know is part of a more complex cosmic reality beyond the 3 spatial dimensions, plus time, that we experience in our everyday lives. We may be like an insect living on the two-dimensional surface of a pond, unaware of the deep and complex reality below it. It may be possible that an unseen extra dimension could intersect our world on an extremely tiny scale. According to some scientists, when particles collide at very high energies, the additional gravity needed to create a micro-black hole could come from the extra dimension. They'll know a black hole is there when they see the shower of particles predicted by Hawking's theory. Its presence will open a brief window to a deeper cosmic reality, while shedding light on the ultimate future of our universe. Based on Hawking's theory, a black hole observed today will take its last gasp when the clock strikes 10 to the 100th years from now, a number known as a googol. That's the end of the universe as we know it. But look beyond that to say 10 to the googol, a googolplex years. If you wrote all the zeros in that number in tiny one-point font, it would stretch beyond the observable universe. Will the great arrow of time have come to rest by then? Not if modern theories are correct. They hold that our universe is part of a much larger cosmic cycle of birth and death, with whole new universes coming into being in the space beyond our own. The time horizons of our universe may well be a blip in this grander scheme of things. Back to Earth now. We are products of the great era of stars and witnesses to its great spectacles of gravity and energy. No doubt there are other beings somewhere out there who are attempting to comprehend the universe. They too may invent the idea of time and develop their own theories on where it's all leading. Their discoveries and ours will not survive the entropy at work in the universe, as we all go the way of the stars, and as our universe gives way to grand new eras in the life of the cosmos. From the fires of a sun's birth, twin planets emerged: Venus and Earth. Two roads diverged in our young solar system. Nature draped one world in the greens and blues of life, while enveloping the other in acid clouds, high heat, and volcanic flows. Why did Venus take such a disastrous turn? And what light can Earth's sister planet shed on the search for other worlds like our own? For as long as we have gazed upon the stars, they have offered few signs that somewhere out there are worlds as rich and diverse as our own. Recently, though, astronomers have found ways to see into the bright lights of nearby stars. They've been discovering planets at a rapid clip, using orbiting observatories like NASA's Kepler Space Telescope, and an array of ground-based instruments. The count is almost 1,000, and rising. These alien worlds run the gamut, from great gas giants many times the size of our Jupiter, to rocky, charred remnants that burned when their parent star exploded. Some have wild elliptical orbits, swinging far out into space, then diving into scorching stellar winds. Still others orbit so close to their parent stars that their surfaces are likely bathed in molten rock. Amid these hostile realms, a few bear tantalizing hints of water or ice, ingredients needed to nurture life as we know it. The race to find other Earths has raised anew the ancient question whether out in the folds of our galaxy, planets like our own are abundant and life commonplace, or whether Earth is a rare Garden of Eden in a barren universe. With so little direct evidence of these other worlds to go on, we have only the stories of planets within our own solar system to gauge the chances of finding another Earth. Consider, for example, a world that has long had the look and feel of a life-bearing planet. Except for the Moon, there's no brighter light in our night skies than the planet Venus, known as both the morning and the evening star. The ancient Romans named it for their goddess of beauty and love. In time, the master painters transformed this classical symbol into an erotic figure, then a courtesan. It was a scientist, Galileo Galilei, who demystified planet Venus, charting its phases as it moved around the Sun, drawing it into the ranks of the other planets. With a similar size and weight, Venus became known as Earth's sister planet. But how Earth-like is it? The Russian scientist Mikhail Lomonosov caught a tantalizing hint in 1761. As Venus passed in front of the Sun, he witnessed a hair-thin luminescence on its edge. Venus, he found, has an atmosphere. Later observations revealed a thick layer of clouds. Astronomers imagined they were made of water vapor, like those on Earth. Did they obscure stormy, wet conditions below? And did anyone, or anything, live there? The answer came aboard an unlikely messenger, an asteroid that crashed into Earth. That is, according to the classic sci-fi adventure, the first spaceship on Venus.
It's really a spaceship from another planet, which exploded in the air before landing.
A mysterious computer disk is found among the rubble.
Was offered access to the world's largest computer to try to decipher this strange language.
With anticipation rising on Earth, an international crew sets off to find out who sent it and why. What they find is a treacherous, toxic world. No wonder the Venusians want to switch planets. It was time to get serious about exploring our sister planet. NASA sent Mariner 2 to Venus in 1962, in the first ever close planetary encounter. Its instruments showed that Venus is nothing at all like Earth. Rather, it's extremely hot, with an atmosphere made up mostly of carbon dioxide. The data showed that Venus rotates very slowly, only once every 243 Earth days, and it goes in the opposite direction. American and Soviet scientists found out just how strange Venus is when they sent a series of landers down to take direct readings. Surface temperatures are almost 900 degrees Fahrenheit, hot enough to melt lead, with the air pressure 90 times higher than at sea level on Earth. The air is so thick that it's not a gas, but a supercritical fluid, liquid CO2. On our planet, the only naturally occurring source is in the high-temperature, high-pressure environments of undersea volcanoes. The Soviet Venera landers sent back pictures showing that Venus is a vast garden of rock with no water in sight. In fact, if you were to smooth out the surface of Venus, all the water in the atmosphere would be just 3 centimeters deep. Compare that to Earth, where the oceans would form a layer 3 kilometers deep. If you could land on Venus, you'd be treated to tranquil vistas and sunset skies painted in orange hues. The winds are light, only a few miles per hour, but the air is so thick that a breeze would knock you over. Look up and you'd see fast-moving clouds streaking around the planet at 300 kilometers per hour. These clouds form a dense high-altitude layer from 45 to 66 kilometers above the surface. The clouds are so dense, Jupiter's moon Io is bleeding lava. It's produced deep underground by the friction of rock on rock, caused by the gravitational pull of its mother planet. Then there's Neptune's moon Triton, with crystals of nitrogen ice shooting some 10 kilometers above the surface. Saturn's moon Titan, with frozen liquid methane and ammonia oozing into lakes and swamps. On our planet, volcanoes commonly form at the margins of continents and oceans. Here, the vast slabs of rock that underlie the oceans push beneath those that bear the continents. Deep underground, magma mixes with water, and the rising pressure forces it up in explosive eruptions. On Venus, the scene is very different. In the high-density atmosphere, volcanoes are more likely to ooze and splatter, sending rivers of lava flowing down onto the lowlands. They resemble volcanoes that form at hotspots, like the Hawaiian Islands. There, plumes of magma rise up from deep within the Earth, releasing the pressure in a stream of eruptions. To see a typical large volcano on Venus, go to Sapas Mons, at 400 kilometers across and 1.5 kilometers high. The mountain was likely built through eruptions at its summit, but as magma reached up from below, it began to drain out through subsurface tubes or cracks that formed a web of channels leading onto the surrounding terrain. Is Venus, like Earth, still volcanically active? Finding the answer is a major goal of the Venus Express mission, launched in 2005 by the European Space Agency. Armed with a new generation of high-tech sensors, it peered through the clouds. Recording the infrared light given off by several large mountains, it found that the summits are brighter than the surrounding basins. That's probably because they had not been subject to as much weathering in this corrosive environment. This means that they would have erupted sometime within the last few 100,000 years. If these volcanoes are active now, it's because they are part of a deeper process that shapes our planet as well. On Earth, the release of heat from radioactive decay deep in its mantle is what drives the motion of oceanic and continental plates. It's dependent on erosion and other processes associated with water. With no water on Venus, the planet's internal heat builds to extreme levels, then escapes in outbreaks of volcanism that may be global in scope. This may explain why fewer than 1,000 impact craters have been found on Venus. Anything older than about 500 million years has literally been paved over. So why did Venus diverge so radically from Earth when it was born in the same solar system and under similar circumstances? There is growing evidence, still circumstantial, that Venus may in fact have had a wetter, more Earth-like past. One of the most startling findings of the early Venus missions was the presence of deuterium, a form of hydrogen, in Venus' upper atmosphere. It forms when ultraviolet sunlight breaks apart water molecules. Additional evidence recently came to light. Venus Express trained its infrared sensors on the planet's night side to look at how the terrain emits the energy captured in the heat of the day. This picture is a composite of over 1,000 individual images of Venus' southern hemisphere. Higher elevation areas, shown in blue, emit less heat than the surrounding basins. That supports a hypothesis that these areas are made not of lava, but of granite. On Earth, granite forms in volcanoes when magma mixes with water. If there's granite on Venus, then there may well have been water. If Earth and Venus emerged together as twin blue marbles, then at some point the two worlds parted company. Earth developed ways to moderate its climate, in part by removing carbon dioxide, a greenhouse gas, from its atmosphere. Plants, for one, absorb CO2 and release oxygen in photosynthesis. 1 square kilometer of tropical jungle, for example, can take in several hundred tons of CO2 in just a year. That's nothing compared to the oceans. In a year's time, according to one recent study, just 1 square kilometer of ocean can absorb 41 million tons of CO2. Earth takes in its own share of CO2. When rainfall interacts with rocks, a chemical reaction known as weathering converts atmospheric CO2 to carbonate compounds. Runoff from the land washes it into rivers and the seas, where they settle into ocean sediments. With little water and no oceans, Venus has no good way to remove CO2 from its atmosphere. Instead, with volcanic eruptions adding more and more CO2 to the atmosphere, it has trapped more and more of the sun's heat in a runaway greenhouse effect. Venus is so hot that liquid water simply cannot survive on the surface. Nor, it seems, can it last in the upper atmosphere. The culprit is the sun. The outer reaches of its atmosphere, the corona, is made up of plasma heated to over 1 million degrees Celsius. From this region, the sun sends a steady stream of charged particles racing out into the solar system. The solar wind reaches its peak in the wake of great looping eruptions on the surface of the sun, called coronal mass ejections. The blast wave sweeps by Venus. Then heads out toward Earth. Our planet is fortified against the solar blast. Plumes of hot magma rise and fall in Earth's core as it spins, generating a magnetic field that extends far out into space. It acts as a shield, deflecting the solar wind and causing it to flow past. It's this protective bubble that Venus lacks. Venus Express found that these solar winds are steadily stripping off lighter molecules of hydrogen and oxygen. They escape the planet on the night side, then ride solar breezes on out into space. All this may be due to Venus' size, 80% that of Earth. This prevents the formation of a solid iron core, and with it the rising and falling plumes that generate a strong magnetic field. There may be another reason too, according to a theory about the planet's early years. A young planet Venus encountered one or more planet-sized objects in violent collisions. The force of these impacts slowed its rotation to a crawl and reversed it, reducing the chances that a magnetic field could take hold. This theory may have a surprising bearing on Earth's own history. Scientists believe the Sun was not always as hot as it is. In fact, going back several billion years, it was cool enough that Earth should have been frozen over. Because it was not, this is known as the faint young sun paradox. Earth's salvation may well be linked to Venus's fate. The idea is that the Earth occupied an orbit closer to the Sun, allowing it to capture more heat. The gravity of two smaller planets with unstable orbits would have gradually pushed it out to its present orbit. The pair would eventually come together, merging to form the Venus we know. As dead as Venus is today, it has brought surprising dividends in the search for life. On its recent crossing between Earth and the Sun, astronomers were out in force, in remote locations where the viewing was optimal, such as the Svalbard Islands north of Norway. The data gathered here would be added to that collected by solar telescopes on the ground and in space. The object for most was to experience a spectacle that will not occur again till the year 2117. It was also to capture sunlight passing through Venus' atmosphere. Today, the Kepler Space Telescope is searching for planets around distant stars by detecting dips in their light as a planet passes in front. Telescopes in the future may be able to analyze the light of the planet itself. If elements such as carbon or oxygen are detected, then these worlds may well be Earth-like. Venus provides a benchmark and some valuable perspective. So what can we glean from the evolution of planet Venus? As we continue to scan the cosmic horizons, the story of Venus will stand as a stark reminder. It takes more than just the right size, composition, and distance from the parent star for a planet to become truly Earth-like. No matter how promising a planet may be, there are myriad forces out there that can radically alter its course. For here was a world, Venus, poised perhaps on the brink of a glorious future. But bad luck passed its way. Now we can only imagine what might have become of Earth's sister planet. Enveloping the other in acid clouds, high heat, and volcanic flows. Why did Venus take such a disastrous turn? And what light can Earth's sister planet shed on the search for other worlds like our own? For as long as we have gazed upon the stars, they have offered few signs that somewhere out there are worlds as rich and diverse as our own. Recently, though, astronomers have found ways to see into the bright lights of nearby stars. They've been discovering planets at a rapid clip, using orbiting observatories like NASA's Kepler Space Telescope, and an array of ground-based instruments. The count is almost 1,000, and rising. These alien worlds run the gamut, from great gas giants many times the size of our Jupiter, to rocky charred remnants that burned when their parent star exploded. Some have wild elliptical orbits, swinging far out into space, then diving into scorching stellar winds. Still others orbit so close to their parent stars that their surfaces are likely bathed in molten rock. Amid these hostile realms, a few bear tantalizing hints of water or ice, ingredients needed to nurture life as we know it. The race to find other Earths has raised anew the ancient question whether out in the folds of our galaxy, planets like our own are abundant and life commonplace, or whether Earth is a rare Garden of Eden in a barren universe. With so little direct evidence of these other worlds to go on, we have only the stories of planets within our own solar system to gauge the chances of finding another Earth. Consider, for example, a world that has long had the look and feel of For as long as we have gazed upon the stars, they have offered few signs that somewhere out there are worlds as rich and diverse as our own. Recently, though, astronomers have found ways to see into the bright lights of nearby stars. They've been discovering planets at a rapid clip, using orbiting observatories like NASA's Kepler Space Telescope, and an array of ground-based instruments. The count is almost 1,000 and rising. These alien worlds run the gamut, from great gas giants many times the size of our Jupiter, to rocky charred remnants that burned when their parent star exploded. Some have wild elliptical orbits, swinging far out into space, then diving into scorching stellar winds. Still others orbit so close to their parent stars that their surfaces are likely bathed in molten rock. Amid these hostile realms, a few bear tantalizing hints of water or ice, ingredients needed to nurture life as we know it. The race to find other Earths has raised anew the ancient question whether, out in the folds of our galaxy, planets like our own are abundant and life commonplace, or whether Earth is a rare Garden of Eden in a barren universe. With so little direct evidence of these other worlds to go on, we have only the stories of planets within our own solar system to gauge the chances of finding another Earth. Consider, for example, a world that has long had the look and feel of a life-bearing planet. Except for the Moon, there's no brighter light in our night skies than the planet Venus, known as both the morning and the evening star. The ancient Romans named it for their goddess of beauty and love. In time, the master painters transformed this classical paradox. Earth's salvation may well be linked to Venus's fate. The idea is that the Earth occupied an orbit closer to the Sun, allowing it to capture more heat. The gravity of two smaller planets with unstable orbits would have gradually pushed it out to its present orbit. The pair would eventually come together, merging to form the Venus we know. As dead as Venus is today, it has brought surprising dividends in the search for life. On its recent crossing between Earth and the Sun, astronomers were out in force, in remote locations where the viewing was optimal, such as the Svalbard Islands north of Norway. The data gathered here would be added to that collected by solar telescopes on the ground and in space. The object for most was to experience a spectacle that will not occur again till the year 2117. It was also to capture sunlight passing through Venus' atmosphere. Today, the Kepler Space Telescope is searching for planets around distant stars by detecting dips in their light as a planet passes in front. Telescopes in the future may be able to analyze the light of the planet itself. If elements such as carbon or oxygen are detected, then these worlds may well be Earth-like. Venus provides a benchmark and some valuable perspective. So what can we glean from the evolution of planet Venus? As we continue to scan the cosmic horizons, The story of Venus will stand as a stark reminder. It takes more than just the right size, composition, and distance from the parent star for a planet to become truly. The blast wave sweeps by Venus. Then heads out toward Earth. Our planet is fortified against the solar blast. Plumes of hot magma rise and fall in Earth's core as it spins, generating a magnetic field that extends far out into space. It acts as a shield, deflecting the solar wind and causing it to flow past. It's this protective bubble that Venus lacks. Venus Express found that these solar winds are steadily stripping off lighter molecules of hydrogen and oxygen. They escape the planet on the night side, then ride solar breezes on out into space. All this may be due to Venus' size, 80% that of Earth. This prevents the formation of a solid iron core, and with it the rising and falling plumes that generate a strong magnetic field. There may be another reason too, according to a theory about the planet's early years. A young planet Venus encountered one or more planet-sized objects in violent collisions. The force of these impacts slowed its rotation to a crawl and reversed it, reducing the chances that a magnetic field could take hold. This theory may have a surprising bearing on Earth's own history. Scientists believe the Sun was not always as hot as it is. In fact, going back several billion years, it was cool enough that Earth should have been frozen over. Because it was not, this is known as the faint young sun paradox. Earth's salvation may well be linked to Venus's fate. The idea is that the Earth occupied an orbit closer to the Sun, allowing it to capture more heat. Earth developed ways to moderate its climate, in part by removing carbon dioxide, a greenhouse gas, from its atmosphere. Plants, for one, absorb CO2 and release oxygen in photosynthesis. 1 square kilometer of tropical jungle, for example, can take in several hundred tons of CO2 in just a year. That's nothing compared to the oceans. In a year's time, according to one recent study, just 1 square kilometer of ocean can absorb 41 million tons of CO2. Earth takes in its own share of CO2. When rainfall interacts with rocks, a chemical reaction known as weathering converts atmospheric CO2 to carbonate compounds. Runoff from the land washes it into rivers and the seas, where they settle into ocean sediments. With little water and no oceans, Venus has no good way to remove CO2 from its atmosphere. Instead, with volcanic eruptions adding more and more CO2 to the atmosphere, it has trapped more and more of the sun's heat in a runaway greenhouse effect. Venus is so hot that liquid water simply cannot survive on the surface. nor, it seems, can it last in the upper atmosphere. The culprit is the Sun. The outer reaches of its atmosphere, the corona, is made up of plasma heated to over 1 million degrees Celsius. From this region, the Sun sends a steady stream of charged particles racing out into the solar system. The solar wind reaches its peak in the wake of great looping eruptions on the surface of the Sun, called coronal mass ejections. The blast wave sweeps by Venus. Then heads out toward Earth. Scientists have identified around 1,700 major volcanic centers on Venus, ranging from lava domes and strange features called arachnoids or coronae, to giant volcanic summits. The planet is peppered with volcanoes, perhaps in the millions, distributed randomly on its surface. Venus is run through with huge cuts thousands of kilometers long that may well be lava channels. Our sister planet is a volcanic paradise in a solar system shaped by volcanism. The largest mountain on Earth, Hawaii's Mauna Kea volcano, measures 32,000 feet from seafloor to summit. Rising almost 3 times higher is the mother of all volcanoes, Olympus Mons on Mars. Jupiter's moon Io is bleeding lava. It's produced deep underground by the friction of rock on rock, caused by the gravitational pull of its mother planet. Then there's Neptune's moon Triton, with crystals of nitrogen ice shooting some 10 kilometers above the surface. Saturn's moon Titan, with frozen liquid methane and ammonia oozing into lakes and swamps. On our planet, volcanoes commonly form at the margins of continents and oceans. Here, the vast slabs of rock that underlie the oceans push beneath those that bear the continents. Deep underground, magma mixes with water, and the rising pressure forces it up in explosive eruptions. On Venus, the scene is very different. In the high-density atmosphere, volcanoes are more likely to ooze and splatter, sending rivers of lava flowing down onto the lowlands. They resemble volcanoes that form at hotspots, like the Hawaiian Islands. There, plumes of magma rise up from deep within the Earth, releasing the pressure in a stream of eruptions. To see a typical large volcano on Venus, go to Sappas Mons, at 400 kilometers across and 1.5 kilometers high. The mountain was likely built through eruptions at its summit, but as magma reached up from below, it began to drain out through subsurface tubes or cracks that formed a web of channels leading onto the surrounding terrain.
Tourism is big business. There's almost nowhere on Earth you can't go. But the ultimate destination may be 100 kilometers above your head. Space tourism visionaries are creating the next generation of holidays that are out of this world. The getaway of the future will be a trip to the stars, the opportunity to rocket far from the Earth. The 21st century spaceman could be you. This could be the ride of your life. The Final Frontier offers the greatest adventure holidays. Check into a luxury billion-star space hotel. Catch a game of football in zero gravity. Or treat your partner to a date with a difference by taking them to dinner, trillions of kilometers from home.
The Wright brothers didn't think there'd be hundreds of people having a meal going to London. I think that in my lifetime you will see resort hotels in orbit.
Stardate 2020. Your dream holiday starts here. Just $4 million buys a seat to fly a couple of 100 kilometers into outer space. This is the Galactic Suite Space Resort. Your room is a super deluxe pod, with zero gravity as standard. And this room comes with the most incredible of views. The resort orbits the Earth every 80 minutes. It's possible to watch not just one spectacular sunset, but 15 every day. And this isn't science fiction. It's about to become science fact. In the Spanish city of Barcelona, a team of space architects are hard at work designing a space hotel fit for the stars. They're backed by a secret investor with $3 billion of cash to splash. And they're already taking reservations.
Never
before has the space been designed for tourists, where their comfort, needs and activities take on a different level of importance. What's important to us is to be amongst the first that can do it.
At his boutique hotel, Xavier plans a 3-bedroom deluxe suite. The hotel will travel around the globe at 30,000 kilometers an hour, 450 kilometers up. Xavier's even planned a holiday wardrobe for the space tourist. Check in and slip on a Velcro spacesuit. And you can attach yourself to a wall like Spider-Man. 38 wealthy wannabe space tourists have already booked their hotel rooms in outer space, even though the plans are still on the drawing board. But across the Atlantic, one man is betting on making your space vacation dreams come true even sooner. Just a few kilometers from the casinos, billionaire hotelier Robert Bigelow is taking the biggest gamble of his life.
I kept it a secret for a long time as to what my real ambitions were, trying to work like a dog and save money and take a lot of risks.
Robert made his fortune in hotels. Now he's set his sights a lot higher. But his plans came as a surprise back at home.
When I told my wife that I was going to do something like this, she said, "You're going to do what?"
Robert's idea is out of this world. He's taking real estate into space, developing a giant space station that gives new meaning to high-rise living. He intends it to be used for different purposes, as a home, an office, or a weekend retreat.
What we're out to do is try to create a safe, affordable environment that's larger and larger for people to do all kinds of things.
Okay, I'm in position, Dave.
Building in space is a costly exercise. The International Space Station cost a whopping $100 billion. Robert needed a design that would be far easier to construct and one that wouldn't break the bank to build. NASA came up with a solution. They were developing a huge, lightweight space habitat that inflates in orbit, making it cheap and easy to launch. But when NASA's research costs spiraled, the project was scrapped. Robert saw his chance and snapped up the plans.
These systems are extremely strong. They're not balloons. Best correlation I can give you would be comparing it to the tire on your car. And it's made up of multiple layers, steel belts, and other kinds of very strong materials. And that's the same way with our architecture.
But would the idea fly? There was only one way to find out. In 2006, Robert launched a prototype, hitching a ride on a Russian rocket.
In my mind, I thought, there's going to be all kinds of things going wrong. We're going to fail.
To everyone's amazement, not only did the station inflate, but it also managed to broadcast extraordinary live footage back to Earth.
Biggest shock was, oh my God, what we're doing is working for real. It can't get any better than this.
Now Robert is building the real thing, a full-sized place in space. The launch party is planned for 2014, and the onboard entertainment promises to be spectacular.
We will also have many cameras on board our spacecraft, and on a large section of wall, see any number of different angles of what's outside, so you could get right up on the moon. Even though you're only in low Earth orbit, you might have the moon right in your face.
With limitless shapes and sizes, inflatable buildings could make almost anything possible in space. Imagine experiencing new sports that can only be played in the zero gravity of space. Join the crowd at the Zero Gravity World Cup in a gigantic orbital space sports stadium.
Come on!
This is the dawn of a new era of space tourism. The sky is no longer the limit. But some have been unable to wait to get their space fix. In 2006, Iranian-American entrepreneur Anousheh Ansari became one of the first space tourists.
I believe that there is something inside us always attracting us to the night skies, maybe because we're made of stardust.
She paid $20 million to take a holiday at the International Space Station and made a video of her adventure.
Just having the opportunity to fly from one end of the station all the way to the other, it was great. And I tried to go really fast and show off that, I'm made to be in space. I'm made to be an astronaut.
Everything on board was pretty relaxed, especially in the dining room.
It's the only place that you're allowed to play with your food. Any simple task that you do on a daily basis, you know, brushing your teeth, drinking water, just eating can be fun.
And in space, there's not much space. But this is a room with a view.
This is my sleeping bag right here, right by the best view from the world. And I can see the clouds, the Earth rotating by. I see the curvature right there. That was actually my favorite time to just, you know, look at the night skies. I felt like, you know, I could live in space forever.
Anusha's trip cost her a cool $2 million a night. But there's good news for the rest of us. In your lifetime, you could be taking your own, more luxurious, affordable space adventure.
10, 9, 8, go for main engine start. 6, 5, 4.
One thing stands between you and the ultimate holiday in space: gravity.
Space shuttle Atlantis, reaching the crest of its historic.
To overcome it costs a fortune. $500 million per shuttle launch. The rockets use vast amounts of fuel, held in gigantic throwaway tanks. It's clear that for space tourism to take off, some clever thinking was needed. So in 2004, millionaire space enthusiast Anusha Ansari set the world a challenge by funding a $10 million competition to create low-cost spacecraft.
The only thing that can drive innovation is competition, to make access to space faster, safer, easier, and cheaper.
Teams from around the world took up her X Prize challenge. But in Mojave, California, maverick engineer Burt Rutan was ahead of the game. He was already working on a secret spacecraft.
Can you do a dog? A dog?
Burt is an aviation legend. You might say he's light years ahead of the competition.
Okay, I'm going to do a lion. Okay, you ready?
He had already built a plane so lightweight, it flew around the globe on a single tank of fuel. And he smashed altitude records with Proteus, which soared to more than 63,000 feet.
Ready to go?
Now, he's set his sights on sending tourists into space.
Listening to those that have been in space, the way they describe it, it seems life-changing to look down on the planet. And a chance to go there and look at that? Wow.
Just 5 months after the X Prize was announced, Burt Rutan rolled out Spaceship One. It had taken more than 3 years to build. To escape Earth's gravity, Burt used an ingenious design, with not one plane, but two. An aircraft would carry the space plane beneath its fuselage and release it at 50,000 feet to rocket into space. Pilot Brian Binney fired the rocket.
Good flight. Good flight.
Holy!
He narrowly missed a collision with the mothership.
That's good, though. 350, suggest shutdown. Roger, shutdown.
Within seconds, he had crossed the boundary into space, 100 kilometers above Earth.
Boy, it's really quiet up here. I'm going to get the camera out. Roger that.
Benny was able to take a few snaps for the album, from the first privately built spaceship to reach space.
RCSC on. Copy that, Brian. It's moving and it's green. The CTN's a little warm, but looking fine. 3, 2, 1, coming down.
The civilian race for space had been won. But for Bert, this was only the start of his dream.
If I could please invite onto the stage Bert Rutan, the designer of the first private spaceship, Spaceship One. Bert?
I'll tell you something. I have a hell of a lot bigger goal. And you know what that goal is? I absolutely have to develop a manned space tourism system that's at least 100 times safer than anything that's ever flown manned to space, and probably a lot more. I have to do that.
Bert's ambitions are shared by billionaire entrepreneur Sir Richard Branson, and together they have set their sights on helping you reach the stars. Thousands of kilometers away, at his private Caribbean island, Necker, Richard puts his mind to taking tourists into space.
I'm old enough to have seen the moon landing, and I assumed that I one day would go to the moon. But the decades went by, and government-run space agencies were not that interested in getting you or me into space. So, out of frustration, we decided to create a private spaceship company where we could get as many people as possible to be able to experience spaceship travel.
This is Richard's dream, to use Bert Rutan's spaceship technology to take you on the trip of a lifetime. On board a spaceplane, you'll jet 60,000 feet up, to then rocket at 5,000 kilometers an hour, up to outer space. Pop your seatbelt and float in zero gravity. Then, check out the amazing views. You'll coast 104 kilometers above Earth for 6 whole minutes, until it's time to go home.
This spaceship will glide serenely back to Earth, and my guess is that quite a lot of them will be itching to get back up again.
Today, rocketing to space isn't for the faint-hearted. Astronauts must train hard to prepare for launch day. They have to be super fit to handle the extreme force of gravity.
2, 1, 0. Booster ignition and liftoff of Discovery.
But Richard Branson's business banks on just about anyone being able to fly, regardless of age or levels of fitness. Something Dave Clark, who must find future passengers, is all too aware of.
What if we had the spaceships and we had all these people signed up and then nobody was actually physically able to fly?
To find out if the average person could jet into space, the NASA Center in Philadelphia has developed a custom flight simulation.
We've developed a centrifuge program to replicate as almost exactly what's going to happen to your body in your trip into space.
GX now, concentrate on your breathing.
And finding out how most people would react has never been done before.
The data that they have on centrifuge is mostly from the military. These are the most healthy, perfectly proportioned, physical specimens of the population. These are Top Gun pilots, whereas we have people's kids, people, overweight people, older people.
Now talk about your gene training profiles.
75 space tourists, including Richard, have volunteered to go for a spin. They are about to discover what 5,000 kilometers an hour feels like.
You got the training, you got the tools, you know what to do. All right, go. You're at Mach 2, climbing at 80,000 feet.
The trainers ratchet up the Gs. This is as close as it gets to the real thing.
You're feeling the rush in the heart, you're feeling the pressure on your chest.
Coming up to Mach 3.
The adrenaline is flowing.
Here's your chance to catch your breath.
Thank you very much.
Richard, tell us, what was it like?
It was wonderful. I mean, it's so important to go through that so that when you actually go into space, you can just lie back and enjoy the whole experience and not be worried about, is your body going to cope?
Richard sails through the test. But will the oldest volunteer, scientist Professor James Lovelock? He's 91 years old and is hoping he too will be able to fly to outer space. Space tourists will feel the power of G-forces. During takeoff and landing, the heart struggles to pump blood to the brain. But with training, it is possible to avoid the dangers. By squeezing your leg muscles, you can improve blood flow, making for safer spaceflight.
Welcome back to Earth, astronaut. You are now our most senior centrifuge rider. You hold the record. Oh, good.
All 75 wannabe space tourists pass with flying colors, proving it is possible to fly into space, whatever your age or condition.
Did well, James.
The G-forces are quite brief, and the centrifuge has now shown that really anybody can do this flight. Stephen Hawkins is planning to go into space with us. He'll be able to put up with it. James Lovelock, the environmentalist, he's going to go into space with us.
Now, it's just a case of saving up to buy your ticket for $200,000.
We've got to try to come up with, clever ways of getting that price down and down and down. Every $10,000 we can get it down opens the market up that much more. And I think 50 years from now, hopefully literally hundreds of thousands of people will be able to afford to go into space.
Richard Branson had the vision to turn space into the ultimate tourist destination. Now, all he needed was a spaceship. Back in Mojave, following his X-Prize win, Burt Rutan and his team started engineering his space tourist dream.
What we're doing is important because it's doing something that's never been done.
Burt's prize-winning prototype, Spaceship One, carried just one pilot into space. There's not enough room for space tourists, so Burt scales up his spaceship and creates a version for 6 passengers. And it's built with the sightseer in mind. Each passenger gets a window seat next to an aisle. It's double the size of its predecessor, so it needs a bigger twin fuselage mothership. But safety is always a top priority.
We can't achieve the level of safety that you do with modern airliners because they've had 7 decades of maturity. However, I do feel that to fly the public, this should not be looked at it as a dangerous adventure.
But modern airliners don't have to re-enter our planet's atmosphere. Anything speeding towards Earth tends to burn up. Bert's determined to ensure his spaceplane will be hundreds of times safer than spaceflight today. So, he has developed a revolutionary way for his spaceship to re-enter the Earth's atmosphere slowly. The spaceplane's wings pivot 65 degrees. Its fuselage flattens into the airstream, creating stable drag, like a shuttlecock. Spaceship 2 is so lightweight and the drag so high, it rapidly slows down without heating up. Then, at 70,000 feet above the ground, the wings realign like a glider, and the craft touches smoothly down on the runway.
My solution was to find the very safest way to land a manned spaceship. To me, it was the simplest way of doing a difficult job.
October 2010. It's taken 5 years to develop Spaceship 2. Today, she's leaving the hangar for her maiden voyage. At Mojave Spaceport, there is only one question on everyone's lips. Will she fly? Richard and Bert have gambled their reputations and a small fortune on the odds that she will. They are about to find out.
Standing next to Bert, watching it get higher and higher and higher. Obviously, Bert was understandably extremely nervous. I was nervous for him and for us.
45,000 feet above their heads, it's the moment of truth.
10 seconds. We are armed.
Release, release.
Clear the plane. Good release.
Okay, it's gone. All good, all good. Beautiful, beautiful.
Yeehaw!
That's great. Beautiful flight.
She flies perfectly.
We got word back that it was flying absolutely beautifully. It was a tremendous moment. You know, we really are close to the dream becoming a reality.
Beautiful job, Pete.
The final frontier is one step closer. Soon, you could be taking your seat on this spaceship for your unforgettable 6 minutes in space. But for these stargazers, this is only the beginning. If they have their way, you could travel on their spaceship to an orbiting hotel for the ultimate space vacation.
A lot of my life has been about dreams. If you don't dream, you don't make anything. One day you might see a giant V floating around the Earth.
The Wright brothers didn't think there'd be hundreds of people having a meal going to London. I think that in my lifetime you will see resort hotels in orbit.
Staying at a space hotel, you can expect more than 5-star luxury. From here, you can gaze on an entire galaxy.
I think the important thing about being in a space hotel is that you have massive windows, and so you can look out at the universe around you and marvel at it.
And once you've been there, space travel agents will be booking your trip to the next holiday hotspot. Have you ever gazed up at the moon, tracking across the night sky, and wondered what it might be like to visit, to fly over its craters, or take a walk across the lunar landscape? At 400,000 kilometers from Earth, it would take you days to get here. So once you get here, you're going to want to stay around. In Las Vegas, Robert Bigelow thinks he can offer you the perfect place to stay. His inflatable space station could open as the first moon hotel.
What you have is an entire station that's really a potential lunar base. We would use low Earth orbit as the trial place of assembling these craft. And with a few modifications, we can turn these stations into bases.
Once you land here, Hotel Moon will offer the latest in cosmic comfort. This is one resort where they really will have thought of everything, including the breakfast buffet. In the arid desert near Tucson, Arizona, feeding lunar tourists is food for thought.
We're going to go to the moon, or we're going to go to Mars or beyond, and we have to survive. And unless we're going to carry a picnic basket of fresh vegetables and processed foods, which we can't do in the long term, we're going to have to grow our own.
If you're going to enjoy fine dining on the moon, you'll need a space food expert like Dr. Gene Giacomelli. He knows how to grow crops that are out of this world.
I find this very exciting, to be able to use agricultural technologies to grow plants to feed people like we do on Earth, but to bring that to space.
On Earth, our atmosphere filters out dangerous solar radiation that would otherwise wipe out crops, rainforests, and woodlands. But on the moon, there's no protection. For crops to survive, a greenhouse would have to be shielded. Buried underground to protect it from the sun, it could nurture crops with very little help from people.
The lunar greenhouse, in many ways, is a robot. It automatically provides its climate so that the plants grow in the way we want them to grow. It provides the temperature and the light, carbon dioxide, as well as the hydroponic system for nutrients and water.
Gene and his team have already built a prototype lunar greenhouse. On the moon, it would assemble itself, pre-packed with seeds ready to germinate. These plants don't even need soil. They can hang inside plastic envelopes, their roots bathed in nutrient-rich water.
But there it is.
Nice roots, Dr. G.
We're growing tomato, sweet potato, strawberry, and lettuce. And this certainly isn't a full diet, but it does offer the crunchiness of a salad, carbohydrate with sugar, and strawberry as a sweet fruit.
Lunar crops will generate drinking water and convert carbon dioxide into breathable oxygen, giving you not just a taste of home, but keeping you alive in space wherever you go.
The system certainly can be used on Mars and the Moon, but why not beyond? Why not in space stations and intergalactic traveling spaceships, providing food and life support for the space travelers?
Getting to Mars on today's rockets depends on planetary alignment. The flight is only possible every 2 years, and the trip takes 7 months. Once there, you wouldn't be able to set off for home until Earth realigns again, 18 months later. So engineers and scientists have been looking for a much faster way to fly. Houston, Texas. Behind these shops, in a seemingly bland warehouse, a multi-million-dollar experiment is underway that could put Mars on your space trip itinerary. Franklin clocked a record-breaking 7 trips on the space shuttle. As the wheels touched down on his final NASA mission in 2002, his need for speed grew. He needed a faster set of wings.
Right off the bat, we know that we need something entirely different, something that would get us to speeds that are maybe 10 times faster than what we could do today.
Scrapping conventional thinking, Franklin throws away the rulebook and works out what the problem with speed boils down to.
The fundamental issue of rocket propulsion is that you want the exhaust to be very hot, and the hotter the better.
So, Franklin cooks up a revolutionary new rocket engine. It's powered by one of the hottest things known to man, plasma, and it's about to be fired up inside this vacuum chamber. The rocket is powered by hydrogen gas, which when heated turns into pure plasma. Powerful magnets push the plasma through the engine to supercharge the spaceship. Plasma is so powerful, you could jet around 4,000 kilometers in a minute and rocket to Mars at 200,000 kilometers an hour, slashing a 7-month flight to just 39 days, with 2 weeks rest and relaxation when you get there. That's a 100-day return trip compared to 3 years flying today's rocket ships.
All my life, I've dreamed about going to Mars and beyond. Space is like a drug, you know, once you get hooked, you don't want to give it up.
In Los Angeles, science fiction is becoming science fact. NASA scientist Dr. Kevin Grazier advises Hollywood on science fiction. And he thinks what you see on the big screen could be just around the corner.
The days of a few astronauts, cosmonauts, going into space, that's over. In the not-too-distant future, we're going to see you, me, regular people going into space.
Kevin thinks science will let us boldly take a holiday where no man has done so before.
A really far-out propulsion system that NASA has actually looked into is antimatter.
Buckle up for a journey on board your intergalactic space liner powered by antimatter. A look under the bonnet reveals a magnetic chamber that contains antiparticles. They're fed through magnetic rings to collide with their nemesis, matter. In just a nanosecond, billions of explosions create an enormous surge of energy, 10 million times more powerful than today's rockets, with a top speed of just over 1 billion kilometers an hour.
Distances to the planets are puny compared to the distances to the stars and galaxies beyond. If we're going to go to places further than our solar system, we're going to have to speed things up quite a bit. Enter wormholes.
Even flying at light speed to our nearest major galactic neighbor, Andromeda, gives new meaning to long haul. It's a 2.5 million year flight time. So if you're going to cruise beyond the Milky Way, you're going to need a serious shortcut.
The name wormhole comes from an apple. Imagine a worm on the surface of the apple who wants to get to the other side. He can do it one of two ways. He can walk all the way around the outside, or he can chew through the middle. The second is a lot shorter, and that's the basic principle of a wormhole.
If we could bend space-time, we could create a wormhole, a time-saving tunnel that connects two places trillions of kilometers apart. Wormholes might already exist and could become your intergalactic freeways to mind-boggling vacations.
One day you might board your shuttle for Wormhole Express at LAX or Heathrow, take that shuttle to your Starliner, and zap!
Do you fancy a vacation trillions of kilometers from Earth? To holiday in a floating city? To soak up a different sun in a distant galaxy? In the future, we may think nothing of traveling throughout the universe. By having fun in space, tourists could create unimaginable new inventions that would reshape our world. Just as the home computer was initially used for simple gaming, it's now the bedrock of our everyday lives.
The people that will be flying in commercial space flights are allowed to be creative. There's going to be 2 or 3 people that come up with something that's called a breakthrough. And all of a sudden, commercial space travel will look completely justified rather than look at, well, these are just joy rides.
Space tourism could take us all to new places and might ultimately ensure our survival.
Earth is the cradle of humanity, but one shouldn't remain in the cradle forever. Single-planet species don't last. Ask a dinosaur.
Pushing out beyond Earth's orbit will truly become a space species.
I cannot envision all of humanity remaining on this planet. Humanity's destiny is in space.
It's not a matter of if the commercial space industry will take off, but when. It was just over 100 years ago that the Wright brothers flew their first airplane, and now we don't think a thing about jumping in an airplane and flying across the continent or across the largest ocean. Today's commercial space pioneers who are just tickling the edge of low Earth orbit are today's Wright brothers.